So I'll share my screen. Last time we talked about network layer, which was concerned with packets, and it was concerned with routing over network. So for example, I have my computer at home. I want to go to Facebook. As a result, my browser needs to send a request to Facebook and get the data back. And it happens by sending the data first from my computer to my wireless router, then sending this data to my internet service provider. The service provider's servers automatically connect to a Latvian national data center, which automatically sees that you want to connect to Facebook. So it routes the data to, for example, Sweden. And from Sweden, the data travels to America through underwater optical cables. And then in America, their national data center forwards the message to Facebook servers or to Google servers. And the message needs to get back. The contents of the web page need to travel back from Facebook, and they go back the same way or maybe a little bit different way, because the network routers constantly update their routing tables. They constantly measure the fastest route from one place to another, and they can also send parts of the messages in different paths if a new path appears and is faster. So for example, I don't know, it's a fun fact, maybe many people don't really know that, but we want to, for example, check out the underwater or subcontinental cables. So let's see. So underwater cables between continents. So the correct name is submarine communications cable. Let's see, maybe there's a map. Oh, this is a little bit different, sorry. This is submarine, but we need transatlantic. What is this? There was this map that shows internet cables. So there are these cables, and if this is the correct map, the cables are used to connect countries with the internet. So here's the thing. If we look, let's say, for example, how can Germany internet communicate to United States internet? So some time ago, it happened through satellites. So from Germany, the signal goes to almost outer space, to the satellite. This satellite maybe forwards the message to next satellite, and that satellite transmits the message back to ground, to Earth, right? So, Germany and America are not connected, so signal goes to satellites and then travel to United States of America. And then on land, it continues its path over cables, right? So satellites seem to be like a good idea because, you can send many satellites in space. They can fly at different altitudes. So one is a little bit closer to Earth, one is a little bit higher. This way, it's, much less probable that they will hit each other and explode. This is why there is so much more space in space than, for example, on the ground, right? Because ground level is just one level. But the problem with satellites is they are really far from Earth. For example, GPS satellites are 32,000 kilometers above Earth. That is the distance. So height, oops, of GPS satellites. So the idea is that, okay, so this is a more precise number. So satellites for GPS are approximately 20,000 kilometers above Earth, and they are calculated in such distance that, you know, they can cover Earth very well. But the problem is the, let's say, for example, Google Maps distance between Berlin and New York. So the distance between Berlin and New York is only 6,000 kilometers, but the distance to the satellites is 20,000. It's 3 times more, almost 4 times more. As a result, the speed of the signal can be high. The signal can travel fast to the satellites and from satellite to satellite and back to Earth. But the problem is that the distances are so large that there is this latency problem. You send a message to Facebook, maybe the message goes really, really fast, but since the distance is very long, you have to wait several seconds until the signal with the speed of light travels to the satellites, to next satellite, back to Earth, and then back the same path back. So there is latency, there is a waiting time, and you know it adds up. As a result, people decided that maybe they should just spend some money. Actually, sending satellites in the space isn't cheap, but maybe, as crazy as it sounds, maybe a good solution would be to have an optical cable going from Europe to America. Of course, if you think about it, wow, there's so many things that can go wrong. For example, ocean is really deep, right? So, you know, that's one thing. Its surface isn't even, it's not flat, you know. Then there are some sea animals, sea creatures like octopus and kraken that can probably damage the wires, maybe. Maybe they, for example, try to eat through them or something like that, you know. But all things considered, people did try, and I think they succeeded. Okay, so could it be submarine? It's underwater submarine cables for internet. Oh, I guess it was the correct thing. So as a result, people are putting cables from country to country under ocean. These are really long cables, but they are made very well, and we can actually, for example, check out this a cross section of shore and of a modern submarine communications cable. So in the center, it has optical fibers, top quality, best optical fibers, and not just one, but many. As a result, many signals can travel in parallel. And I don't know, I think that each cable can carry several signals at different frequencies. Uh, so, you know, it's like a small cable, but it actually can carry a lot of information through it. And then you have petroleum jelly. So petroleum jelly is a lubricant, a cheap, relatively cheap material that just works as oil. So, you know, this cable, for example, moves a little bit, and there's oil which lubricates it, and the cables don't break, for example, during the installation process and also during transportation. So there needs to be some, for example, petroleum jelly that, you know, prevents these cables from rubbing against each other and being damaged. So then you have copper or aluminum tube. Then you have polycarbonate. It is a plastic, but unlike regular plastics, it's very durable. Then you have aluminum barrier against water. Then you have stranded steel wires, and these are for mechanical strength. So, uh, these optical fibers, they would break. Jelly isn't also a very good material. Then this copper is actually, it's rigid, so it can be broken. But here you have cables. Also, plastics aren't very durable, but these cables, which are stranded, they let this cable to be somewhat flexible, at the same time very strong. So you can twist it a little bit and it will not like break, and it gives the strength. And then you have mylar or PET tape and polyethylene, just plastic, some very good strong plastic around it. So this is the construction of a cable that goes from one continent to another continent. As you can see, modern cables are typically 25 millimeters, that is 2.5 centimeters in diameter. Many of them are actually laid in the sea by private companies, and that company, for example, let's say Google wants to have the fastest user experience. They're really rich, so they can just buy and lay their own cable, and only they use this cable. As a result, you get, for example, their services extremely fast, while other services use satellite or some public cables, and they're not so fast. So big companies are actually interested in supporting the cable network, and then they can get faster user experience and more clients. Okay, so Transatlantic, these are some old. Actually, cables were also used in olden days, for example, this transatlantic telegraph cable, because how else could you send messages from Europe to America? Well, with radio, maybe, but I think at these times, radio wasn't even an option, so they only could use cables, and this is how they could telegraph the messages. This is something old. Yeah, and in modern days, it's of course optical cables. And of course, since the signal travels a long distance, in some places they also need repeaters, some electronics that amplify the signal, and so on. Let's see, is there a map? Okay, here's an interesting thing about how cable is repaired. They take them out of the water, and then they repair them on the ship, and then they put it back underwater. So yeah, there are these cables that are put, between continents, between countries, from America to Australia to China, all these locations. Because on the land, you would have regular optical cables. Okay. So that is all about network layer. So network layers are network layer in Internet protocol is concerned with sending data, and in Internet, each network participant has an IP address, and addressing is through the IP address. So you go to, for example, Facebook, get IP from domain. So there are these online services where you can write domain name. You write, for example, facebook.com, and Facebook, for example, has certain IP address. You can use the same IP address to go to it, um, because these names are just alias to the IP address. And when you connect, your message goes from one computer to another. But so there is a possibility that you have several connections between two computers using different services. For example, you can use Skype to chat with another person, and you can use Dropbox to send files to another person, or email or something like that. As a result, a network layer is only concerned with communications from internet cable or Wi-Fi card to another device. And to service multiple communications, we need to introduce this so-called transport layer. For example, I have right now open Zoom and also internet. Network layer is not concerned with it. It is the transport layer's task to send the data between 2 points on a network. And the transport layer is concerned with segmentation, which means if you need to download a big file, it will chop the file up in several pieces and send the pieces one by one. And the receiver has to put them back together in the correct order, right? Because, for example, you are downloading a movie, and let's say one piece of the movie just, was lost. For example, the router somewhere along the way was shut down and the message disappeared. Well, this transport layer needs to do acknowledgement on the packets that are received, and the sender needs to retransmit the segments that it didn't receive acknowledgements for. And then there's also multiplexing. It means uh, send data from several clients over the same network to several other clients. Okay, so it's good to know that this transport layer exists, and there are some standards that are specifically concerned with the transport layer. In the internet, there are two transport layer protocols that are used, and we will look at them. We will not really look at other ones because these two are used for the internet. And you should just kind of remember these terms. One of them is called Transmission Control Protocol, or TCP. And the other one is called User Datagram Protocol, or UDP. And basically, Transmission Control Protocol is connection-oriented protocol, which would work just as you would expect. The transmission control protocol is used in internet. So for example, you want to connect to some server. So transmission control protocol describes how your computer finds the server on the internet, and then it first says to the server that it wants to connect. The server replies that it accepts connection. Then you can send your data, and on each data, the server sends back that it has received it, acknowledgement. If it didn't send back acknowledgement, this transmission control protocol tries to send it again. If it was received, it will receive acknowledgement. And at the end, for example, client or browser, after downloading this web page, for example, the browser automatically sends to wikipedia.org that it ends the communication. It ends the connection. Right now, this web page is in my computer and I'm not connected to Wikipedia anymore, right? So when I type in this address and hit enter, the browser connects to wikipedia.org. It says, give me this web page, transport layer web page. Wikipedia sends it back. Browser says, thank you, and ends connection. And Wikipedia also closes this connection on its end. So here it is, connection-oriented communication. It needs to give you a reliability and same order delivery, because network layer doesn't generally guarantee that packets of data will arrive in the same order that they were sent. Most of the time it happens so, but as I mentioned, network layer, for example, sends data through, I don't know, one cable underseas, but for some maintenance reasons, suddenly this cable loses power. So network layer would have to find another route and send it through a different route. And it can happen, and then you lose this delivery order because some packets were lost and some weren't. So this is what the transport layer needs to do. Transport layer also is concerned with flow control. It basically, this is why the message or the movie that you are downloading, it is chopped on in smaller pieces and sent piece by piece. So that you send, for example, 1 megabyte of movie, and the receiving computer gets it, then it writes it to the hard drive, and only then it sends back, okay, thank you, send me next megabyte of the movie. Otherwise, for example, if you just send data, maybe the receiving computer cannot is not capable of writing it to the hard drive fast enough, and the communication just becomes uh, damaged. So this flow control is really important. Next is congestion avoidance and congestion control. Uh, it's almost the same. Oh, but one thing is important. Let's say you have a network, and two computers use the same router and they send the messages. What happens if some server is shut down? Well, the problem is that then the senders don't receive acknowledgements and they all retry sending data at the same time, which becomes even worse because then if so many computers try to uh, generate the connection all at the same time, all of their messages will just make a big make a big congestion, and the server can just not be able to manage them all, and you will get this congestive collapse. As a result, actually, in networks, if you send a message and you don't receive a reply, you shouldn't just immediately retry the connection again, because there's a high probability that if the server was busy a second ago, it's probably still busy. As a result, in network, there is this idea that you send a message, and if the server doesn't respond, if the message is lost in the network because some router was overly busy, you wait, for example, 1 second, and then you try again. And if it didn't go through, you wait 2 seconds. And if it didn't go through, you wait 4 seconds, 16 seconds, 32 seconds. Every time you retry, you increase the waiting time so that you don't participate in making the network even more congested. Okay, this is actually how Ethernet worked. Um, well, it's updated now, but the idea was exactly this. You wait 1 second, you wait 2 seconds, you wait 4 seconds, 8, 16, and I think up to 32, if I'm not mistaken. And if after all these retries you still don't reply, then you say, okay, impossible to connect to the server, connection failed, right? So this is congestive collapse. Okay, and here's the multiplexing part. So we have, for example, we have many applications running on our computer, and each of them uses an internet connection. But we only have one Wi-Fi card. So how can Windows computer, for example, manage several connections at the same time? And it's done through multiplexing, and each client opens something called port on the operating system. So let's just check out. So my computer has an IP address, which I can actually try to find. Let's see. How to find an IP address in shell. So let's see, command prompt, and you can write this ipconfig all in your command prompt. And this will show all of the information about my computer's wireless and wired card connections. So right now, my computer is connected to the internet through Ethernet adapter. I have cable plugged in because I have 1 gigabit internet and 1 gigabit cable connecting a computer to the internet. So if I connect it to Wi-Fi, Wi-Fi speed is only something like 300 megabits. So having cable, my internet is 3 times faster than Wi-Fi, so I'm using cable internet whenever I can. And basically this says that my IP address is this, right? So domain name servers. So when computers want to find my computer on the network, they would use this IP address. But since I have multiple applications running on my computer, each of these applications is actually using a sub address of my IP address. They are using ports. And let's check out. In computer networking, port is just, a virtual number in your Windows machine, which accepts communication from certain application. And let's just check out common port numbers. Port 80. When you connect to the internet, the server uses port number 80, right? And the same server can also serve this internet message access protocol. It can also serve email. So for example, you can at the same time connect to google.com and search for information through hypertext transfer protocol, and then you connect to Google's port 80, and at the same time you can also browse your Gmail through, for example, this mail application, and this mail application will be using port number 143, Internet Message Access Protocol, IMAP, or older version is Post Office Protocol, port number 110. And this is how different applications can work on the same computer, on the same network card, on the same IP address at the same time. And nowadays, actually, all internet pages, almost all, are secure, and they use HTTP secure port over TSL SSL, which is 443, port number 443. So actually, it would be like, I don't know, IP address. In a web browser, it would look something like IP address like this, and then you would put column, and for example, port 80. It would mean connect to port 80. I think that if I try the different port, it doesn't, for example, work. So this IP address is IP address of my wireless router. And for example, using this IP address, I can connect to my router and modify its settings. So I can use it using an internet cable. I don't have to connect via USB or something like that. I connect to my router using the IP address that is written on the router's label, and the browsers always by default actually secretly add that they are connecting to port 80, right? So even though I wrote IP address as is, actually browser always by default connects to port number 80 because port number 80 is for internet connections. If I try to connect to the router using different port, for example, 100, well, as you can see, this page didn't load because my router is not listening to port 100. Let's see, for example, 443. I don't know, maybe this router supports it, maybe it doesn't. But let's just check out what would be the IP address of something. DNS lookup. I don't know, let's try the same. For example, google.com. Oops. So I write google.com, but actually in the internet, there is this service called DNS, which is domain name service, which translates first this text actually to the IP address. And actually my browser secretly connects to a page like whatismyip.com, and it asks, I want to talk to Google, what is Google IP address? Because actually servers are addressed by IP address. And there are these services that basically tell, well, Google IP address is this. So it should be that if I copy this address, it should open Google. You see, it opened google.com. I actually wrote the IP address, but it opened me google.com and it beautifully puts this text, but actually it has this IP address. And to make google.com work faster, Google actually has bought 6 different IP addresses which are used randomly. For example, let's say that hackers want to attack google.com and break it down. If Google only had one IP address, then hackers would just make 1 million connections to this address, and Google servers would probably not be able to manage so many connections, and they would just, you know, freeze, or maybe the computer would just reset. But since Google has 6 IP addresses, or maybe even more, no, at the moment it's just 6. and it automatically distributes the connections between these 6 servers, it's much harder to, for example, destroy google.com or make some denial of service attack, because it has 6 different IP addresses. And as soon as one of them gets overly congested, it automatically forwards to the next freest IP address. So let's see, for example, what is the IP address of this thing? Let's just check out. So problem is that if you really think about it, how many IP addresses are there in the world? So IP address version 4 is only 4 bytes. So it's actually 2 to the power of 32. So it's just 4, so this is 1,000, this is million, this is billion. 4 billion IP addresses. As it turns out, it's not a very big number, right? So many hosting services, they host several domains on the same server. And so this domain name service, when it makes calls to IP address, it also actually tells which website it means, because, for example, this colos.lv, it's hosted on a server that hosts several web pages, actually several thousand web pages. So here it says, sorry, blah, blah, blah. You're trying to connect somewhere. Not working. Not working, and so on. So domain name service is a little bit more advanced now. So but it just uses this metadata, and connections are possible. So anyway, these are some common port numbers, but generally you can select any port from 0 to 65,000. It's even written somewhere here. So port number is a 16-bit number. Oh, here it is. I don't know. Its usage in universal remote location address. Mm-hmm. So when you create your own server, for example, you want to make, as this subject suggests, we're talking about a data transmission in wireless sensor networks. But oftentimes, all these sensors are just trying to send information to the server. So you build sensors, you build a server, and you want these sensors to send information to your server. And this information is not really hypertext. It's not really a mail service. As a result, the well-known ports are those from 0 to 1023. If you want to make your own connectivity, you would just select a port that is bigger than 1023, for example, 20,000. And then you can configure your server that it opens a port for example, 20,000. And then the devices connect to port 20,000, and their information that they send is processed by server, like in a separate, part, not interfering with other things. So that is the port. Okay, so transport layer is concerned with ports. When you want to connect, you use IP address for network part, and port for this transport layer part. It is connection oriented, reliable, and so on. And that is the transmission control protocol. Let's see what else can we see on this TCP. So here's the TCP segment structure. So when I try to connect to Facebook and it sends me a lot of pictures and a lot of messages and everything back, this information is split into TCP segments. And we can see the TCP segment header, how it looks like. So if I connect to Facebook, it automatically connects either to port 80 or to port 443 for HTTPS, right? So this is source port. And destination port is similar, so that the receiving and transmitting computers, they know which application requested or sent the data. So these are ports. Then you have sequence number. As I said, maybe the messages didn't arrive in the correct sequence. Well, then this TCP protocol can manage this thing. For example, if it receives a message which has wrong sequence number, for example, the sequence was 1, 2, 3, 4, 7, then, for example, TCP layer in Windows can say stop, send me once more sequence number 5, and it just deletes sequence number 7 because this message arrived way too early, and it could buffer it, or it can just delete it and ask send me once more starting from sequence number 5, right? And retransmit the data, so that because if you put them together in wrong order, of course nothing good will happen. Then there is also this acknowledgement number, so that the receiver, the sender, when it sends the message and gets acknowledgement, it needs to know to which message this acknowledgement comes for. For example, you send messages 1, 2, 3, 4, you receive acknowledgement number 2, you know that message part number 2 was received, and so on. Then you also have several flags like data offset, window size, and so on. Also checksum, just as we talked. Checksum is only 2 bytes long. It is sum. It adds up all of the bytes and all of the overflows. So it's checksum algorithm that we studied several weeks ago. And there's also this urgent pointer. Urgent pointer is described here. If the urgent flag is set, then this 16-bit field is an offset from the sequence number indicating the last urgent data byte, and so on. TCP protocol is, well, it's rather advanced and complicated, and it was invented a long time ago. I don't know if there's a date. Oh yeah, so basically it started in 1974. So it was, developed long time ago, and it has been polished. So you don't have to write this protocol yourself. Usually you would just use libraries. You can find TCP library for embedded systems, and you just add it to your code project and you use it. But you should just understand that you need to use this TCP protocol. You need to know IP address and you need to know the port. And then there are just these high level application programming interface calls, which are managed by operating system or by your library. And here it is. For example, if it is a server, you just issue a listen command. For example, you can make a Raspberry Pi server that services something like a smart switch. You connect to your Raspberry Pi with your cell phone, and you can press some button in application, and the Raspberry Pi switches on or off the lights. So Raspberry Pi would be a server. In its operating system, your code would tell Raspberry Pi operating system to listen, and it just opens a port and waits for a connection, right? Then there is this SYN send. So this is, I'm sending a request to Raspberry Pi computer, and I'm waiting for reply that it received the message and that it has opened a port for me. Then there is SYN received. Established means that data can be delivered to the user. There's also wait 1 and wait 2, close, closing, last acknowledgement, and closed. There's also this flow. So initially, everybody is closed, server is listening, server receives a request from client, and it sends back acknowledgement that it's waiting. If the client receives acknowledgement, then it goes to established mode, and you can start sending data. And after that, you can just close the connection. And usually the general idea is that this relationship between devices is client-server relationship. Client makes a request and the server replies. For example, right now, if I write Wikipedia in my Google, I send a request to Google to search for Wikipedia, and Google sends me a reply with this web page content. Google cannot suddenly send me more data. It's only if I ask data to Google, Google sends me a reply. I ask for another web page, it sends me new data. But it's impossible for Google to somehow secretly connect to my computer and to do something, some damage. It doesn't work that way. So it's a send, request and reply, send and receive relationship. For example, if you open messaging application, actually what happens is your web browser sends a request to server every, for example, 1 second, asking, do you have new messages? And the server will say, for example, no, I don't. No, I don't. If a new message appears, the server replies, yes, I have a new message, and the new message is shown on the screen. But generally, browser just sends requests, for example, every second, asking for new information, and the server replies either with new information or saying, I don't have new information, right? This is important to remember. And usually the refresh time is something like one second or 500 milliseconds and so on. Oh yeah, here's also this. This is closing connection. Closing connection. So initiator sends, I'm done. This says acknowledgement, and this says acknowledgement one more time, so that they both sides know that the connection is closed. So here's a little bit information about maximum segment size. In TCP, I think it's something like 8 kilobytes. The maximum segment size, the largest amount that TCP is willing to receive in a single segment. And it should be approximately the same size as network network layer messages, because then the network layer doesn't need to split them into smaller pieces. But generally, this is done by operating system. You will probably never change the segment size. You don't care about it. Also, the messages are time-stamped so that you know in what order the messages are received, and so on. So, and as we can see, TCP has some vulnerabilities. For example, denial of service. As I said, for example, here's the risk actually. And it has been spoken about for many years already. And you know, one day it will happen. So the easiest way how to attack a website is to plant a virus, a computer virus in many, many computers that just sits there and does nothing until the hacker sends a command to millions of computers to try to open the same web page at the same time. For example, right now I type google.com and it opens, right? But let's say that 1 million or 10 million computers would try to open the same web page at the same time. It would just not work because it would have to service 1 million connections and maybe it takes several seconds. But these infected computers would try to connect maybe 10 times per second to the same web page, and this web page would of course break. Well, it wouldn't really break, it would just become really, really, really slow. Because if I write google.com, my request is put in Google servicing queue, but maybe if there's 1 million computers in front of me in this queue, it maybe takes 10 seconds to service them all. And then these computers try to connect again, and then it's another 10 seconds for another connection. So this denial of service is the most dangerous attack. And the problem is that you have computers, right? So, you know, computer can be infected by a virus. But then you have smart washing machines, smart dishwashers, smart microwave ovens, I don't know, smart doorbells, so many smart devices, all connected to the internet so that you can control them remotely. But what if they also get infected by a virus, which also requires them to connect to the same web page all at the same time? You know, it's a little bit dangerous. It's not necessarily always possible, but you know, if you're building a Wi-Fi powered device, you should kind of consider where you get your chips from. How can you know that, for example, the chips that you are using actually don't have a secret virus inside of them by the manufacturer, right? And well, most of the times, practically, I would say all of these times, it's not really an issue, but it can become an issue. So let's see. I will just give you an example. There was this big scandal in in IT world when something really strange was caught. So so the idea was the following, and this is a real thing, real scandal. Unfortunately, most people don't understand anything from computers, so they, you know, most people don't really understand this thing. But the idea was the following: American company ordered something like 10,000 motherboards for their servers. They send the pictures of the motherboards, the components, to China manufacturers, and they would basically make these PCBs and solder the components on the motherboards and send them back. You know, basically all of the manufacturing is done in China. All right, so it's a regular thing. But these motherboards were actually specifically built for data centers, the ones that manage Facebook or Amazon or these big companies. And these motherboards would also, for example, process credit card data, right? Or personal messages. These messages are stored somewhere, for example, on such motherboards, on hard drives connected to these. And one day, one of these companies received from China the motherboards, and one guy accidentally noticed that there is one small tiny chip on the motherboard that shouldn't actually be there. And it was actually built by company Supermicro. It is actually, it's not like, it's a not known name like Apple or Amazon, but actually Supermicro, I don't know if it still exists, but it was extremely big motherboard manufacturer in America. So since China manufacturing so cheap, Supermicro actually, at the time of this happening, they only had engineers in America, but actually all manufacturing happened in China. And one guy just noticed that on the motherboard, there's, for example, a chip that shouldn't be there, you know. And the problem is, for example, you have processor, you have hard drive, and this chip is put on the data lines. So this chip can actually read all the data that is sent from processor to hard drive. And it can also inject its own data, right? So, okay, so this is a problem. And if you are, for example, making a smart device, what if you order your smart washing machine, but the manufacturer has actually put some chip which turns your device into a potential security threat, potential attack point to do denial of service attacks on some web servers. I don't want to point fingers, right? But for example, and I actually use this chip. I just wouldn't use it for top security um, applications, but there is this ESP32 chip, which is extremely cheap, extremely cheap Wi-Fi module, which runs on, which you can use for Arduino applications. And it's a pretty cool thing. So you can buy this module for something like €3. It has Wi-Fi, it has antenna, it has all kinds of chips on it, also flash memory, and basically you can program it in Arduino environment, and you can instantly make Wi-Fi applications. For example, smart light switches or something like that, smart home on Wi-Fi. This is very, very popular, and it's getting more and more popular because it's really, really cheap. However, well, how can this technology cost only a few euros if other companies are producing the same or similar devices costing, for example, 20 euros? So I personally am a little bit suspicious on this company. It's a joint venture between China and some other. Basically, yeah, here it says ESP32 is created and developed by Espressive System, a Shanghai-based Chinese company, right? So China makes and sells these really, really cheap Wi-Fi chips all over the world, which you can easily implement in your devices. But how can we know that this chip isn't really spying on us, right? Actually, we cannot know it. So if you build a device for military, well, you shouldn't really use it, right? Based off just suspicions. However, if you're making something really simple, you can just use it and don't worry, and it's really cheap, and you will make a very cheap device. But we don't know what's inside there. And you would call this conspiracy theory until these guys detected that Chinese manufacturers have put some spying chips on their actual motherboards. And in this case, this chip is big and you can see it with the eyes. But let's see, blah, blah, blah. Later, they started to put chips this size, okay? So extremely small, you can barely see them on the motherboard. And the next level, so let's see the pictures. The next level thing was that Chinese implanted these chips between the layers of PCB. So they would make a small hole in the PCB, put the chip inside, and then paint over the green color so you wouldn't even see that thing with your eye. You could only see it if you did an X-ray on the motherboard, but how would you know that you have to do the X-ray, right? You can't. So this thing is, pretty crazy. And actually, that was a huge scandal in a technology world. Well, but the only problem is that since most people don't know anything about technology, this didn't go to mainstream, right? But that is what actually happened. Uh, the problem is that this chip that was found implanted on the motherboard is so small. Uh, Actually, we don't really know what this chip does. Maybe it is a spying chip, maybe it isn't. What we do know is that it was put on data lines between CPU and I think random access memory or hard drive. It shouldn't be there. And, we have no idea what this chip does. But I'm just saying that you should be cautious if you are using some really, really cheap technology from China, like this ESP32 device, on some, critical devices. I don't know, medical devices or military devices. You don't really want to do that because there is some a possibility greater than zero that this chip also contains some software that can be activated by the makers of this chip. Okay, so I'm saying it because these chips theoretically could be used to do this denial of service if, for example, your smart dishwasher and your smart microwave oven and your smart whatever device all try to connect to, for example, google.com at the same time, thus making google.com extremely slow and, not allowing people to search the information that they need. Okay, so next attack on TCP could be connection hijacking. It's possible, basically, TCP was never made to be secure. So basically, an attacker can catch these TCP packets, for example, some infected router. It can read them and it can put, for example, modify the data, delete your message and put its own message and send it forward. So TCP is not secure, but it never was made secure. It was never intended to be secure. So it's not really a big problem. but generally TCP packets can be, I would say, damaged or counterfeit. Okay, and so on and so on. And well, that would be generally all about TCP packet. And there is this TCP version 6. The idea is that 4 bytes TCP IP address is too short, so people just expand IP address to version 6, which would be that IP addresses are, I think, 8 bytes long. Let's see. Oh, it's 128-bit address. That's a very long address. Calculating to bytes, it is 16 bytes long address. The number of IP addresses would be so big that it would be almost enough for thousands of years for people half the space. Okay. And, you know, in all fairness, I need also to mention that transport layer uses not only transmission control protocol, but also user datagram protocol. And user datagram protocol is the absolute opposite of transmission control protocol. Transmission control protocol is connection oriented. You first ask a server to respond. The server says, okay, I accept connection. Then you send the data. The server replies. And then you say, I want to end the connection. And the server says, okay, connection ended. And you send back, thank you. And you both delete the connection. The user datagram protocol is totally opposite, and it has no connection at all. You just send a message to server, and server immediately replies. The advantage of UDP protocol is that it's much faster. You just send a message, you get the reply. The disadvantage is it's not connection oriented. So you send a message, maybe you don't even get a reply because the server is not on. So let's see a little bit more information about user datagram protocol. Here's UDP Datagram Header. As you can see, header is much shorter. So in the header, you only have source port, destination port, length of message, and checksum, and that's all. In TCP, you had message number, and so on. Since user datagram protocol is made in such way that each message fits into one datagram. These are short messages, so all of the data is sent in just one message. You wouldn't really use UDP to download movies, for example, because you need to download all of the parts of the movie and in the correct order and so on. But if you want to chat with somebody, or I don't know, use some fast service, you could use UDP because it just sends data and either gets or doesn't get the reply. And this UDP, user datagram protocol, is used, for example, to resolve the IP address. If you write, for example, Facebook in this, or for example, Google, browser uses user datagram protocol to get google.com IP address from these special domain name service providers, domain name system. So there are these, each country has a central entity that manages these domain names, and my browser would connect to my local domain name system management server. Their IPs are fixed and well known to everybody. And it just receives the reply that, for example, Facebook IP address is 555.333. So domain name system is organized in such way that you can buy a domain name. It costs approximately 10 euros a year, and you can just go online, type in that you want to, for example, buy a domain name called I love Donald Trump .com. This is like as a joke. You can search for it. If it is free, then you can buy it. And then you can also pay some server and connect this domain name to the server, and this will be online. By the way, I think .com doesn't really work. Okay. So, this is like just a joke. You don't have to like explode or something. But generally, you can buy these domain names, and then when you open your browser and type in the domain, the browser asks the domain name system issuer what is the actual IP address of that domain name. It receives it, and then it connects. But these domain name system servers, to make them work faster, they are using these user datagram protocol. Because if every time somebody goes on the internet and types in address of a web page, and then you have to open the connection, send the data, close the connection, it's 3 times slower, and the internet would be really slow. But this domain name resolving protocol uses user datagram protocol, and it works faster. By the way, another usage for user datagram protocol is protocol to get time. Let's say your computer doesn't know what time it is and it needs to synchronize the time. Well, if you would use TCP, you first open the connection, then you ask for time, then server sends it back, and then you close the connection. This would be really slow. So user datagram protocol can also be used on time synchronization protocol. For example, this network time protocol, and you just ask the time and it replies immediately without making any connections. So right now here we can see it's transition oriented. For example, network time protocol, it provides datagrams. Simple, it's really simple. And it is sometimes used for bootstrapping to open a real connection. For example, initially you start with UDP and then you go on to a more complicated protocol later. It's also stateless. You don't have to remember, are you connected? Are you disconnected? What state you have? It has no retransmission delays, so it works for real-time applications. For example, this Zoom conference that we have most probably is using UDP, because it doesn't matter if you have a small glitch in audio. If, for example, I say something and some parts of my text came in different order, right? I don't know, you would hear some noise maybe, but it's not so critical. However, if this was TCP protocol, I speak, some server gets slow, and then my voice would sound really weird, because in these real-time applications, it's more important to receive any data than to have, like silent times. Also, user datagram protocol is used for computer games. When you play Counter-Strike, it would be very laggy if, for example, someone's computer is a little bit slower and then all the computers need to wait for that one computer. So, okay, so you missed one packet, it doesn't matter. In online games, it's better that you have fast response times than that you receive all data perfectly. Yeah. Also, user datagram protocol supports multicast, where you basically can send the message to multiple devices. And the maximum size of UDP is 65,000 bytes, I guess. Okay. It also has some checksum computation if necessary. For example, in Internet Protocol version 6, UDP, it has a little bit bigger header, but still very simple. It's just source address, destination address, source port, destination port. This is just zeros. Then it says what protocol it's using. For example, time synchronization protocol or some computer game protocol. Then you have the length of this all message, including the header. Then you have some data length, checksum of the header, and then you have the data. But this header is still smaller and simpler than TCP header. Okay, so that is, I guess, all about TCP and UDP, which is part of transport layer protocols. TCP is reliable. It manages acknowledgement, retransmission, and timeouts. UDP doesn't do that. You send a message, maybe it went through, maybe it didn't. So, it doesn't matter. TCP is oriented and ordered. So if you send two messages and for some reason first message went through satellite and the second message the first message was sent through cable and the second through satellite, as a result, you get them in opposite order, TCP would switch them back and get them in the correct order. UDP doesn't care because each message is separate message. They should not be like relying on each other. TCP requires 3 packets to set up a connection before any user data can be sent. UDP has no connection. Just send data, get back information. And in TCP, data is read as byte stream. You don't know where the message starts or ends. It's just one byte stream without boundaries. UDP is the opposite of everything. Okay, so do you have some questions? You can type them in the chat box.
Professor? Hello.
I hear you.
Yeah, you are speaking about the ESP32, right? Like from the Chinese manufacturers.
Yes.
So, though it's vulnerable, is the import, like, the import customs are still allowing it, or?
Okay, so the thing is, since we don't really know if it's a good or bad chip, you can buy it. You can go
Okay.
online and you can buy it, no
Okay.
problem. It's
Okay.
just, it's just something that you would remember and maybe you wouldn't use it for military projects.
Oh, fine.
It's
Okay.
not a bad chip. Actually, I have used this chip in 2 of my projects. You
Okay.
know, some heating remotely controlled heating application and air quality sensor. I built air quality sensor and I
Okay.
used this ESP32 chip inside, right?
Right.
maybe I wouldn't use it for, I don't know, some security applications.
Fine. Yeah, I understand. Yeah, just like, just was asking. Thank you. Yeah.
Also, we can just go online and check out what the price of this chip is. For example, there's this
Okay.
website.
Yeah.
I can buy these chips from this website, for example, ESP32. I order by price. And I can buy a single chip, but they also sell these really awesome modules.
So bulk. Okay. Okay.
And check it out. It only costs €2.45.
45. Yeah.
It's unbelievably cheap. I mean, come
Yeah.
on.
So I guess that like instead of buying here, you could get it from the Chinese manufacturers like AliExpress or Banggood. It will be even more cheaper.
Mhm.
Yeah.
I mean, this material costs
Mm-hmm.
more. This
Oh, okay.
metal costs more than 245. How is it
Yeah.
possible it's so cheap? I don't know.
Maybe they would have used some recycled materials or cheap quality stuffs.
Uh-huh.
Maybe.
Mm-hmm. Possible. But they're really good
Yeah.
in that sense. Easy to program, really, really good chips.
Yeah.
Okay, some other questions maybe?
That's it, Professor. Thank you.
Mm-hmm. Okay, if no more questions, then we can finish this lesson and, meet next week. Okay, so goodbye.
Professor, regarding the
Yeah.
videos, has it been uploaded